Good morning, everyone. My name is Tony Saad. I'm a faculty in chemical engineering, and welcome to the University of Utah. Very good choice, by the way. I'm sad that I'm unable to be with you today, but I'm currently conducting measurements at the Utah Abravanel Hall and Capitol Theater. More on that in a second. I wanted to introduce you to my group as I am actively recruiting a PhD student. I fall under the general umbrella of scientific computing, starting from computational fluid dynamics and all that comes on top of that, including the transfer of energy, reactions, and chemistry, etc. So we do turbulent reacting flows in the incompressible regime to the low Mach variable density regime. You'll learn more about that as you take your classes with us over here. My group is currently growing. I have two PhD students and I have a few undergraduate students moving in and out. In summary, I have about 3, 4 projects currently very actively researched, and they span all the way from the fundamental scientific computing research to the very applied. And I really like that spread because I can help my students find their passion and throttle between what they like and what needs to be done in the group. Currently on the list of items to be done is first project has to do with very fast CFD solvers. So this is highly mathematical and fundamental type of research into computing. And we just actually developed low cost third order time integrators for Navier-Stokes that are up to 50% cheaper than standard methods. This has tremendous implications as we roll these things out. Especially with high performance computing. On the other spectrum, with more applied work and venturing into experimental research is a project on the effectiveness of drones in measuring particulate matter. So essentially using drones, putting a sensor on a drone, flying a drone and taking a measurement. The question is, how does the airflow around the drone affect those measurements and depending on the particle size and or concentrations, etc. We have some surprising results that are currently being published, and essentially we've shown that sensor location does matter and can be biased by the drone. But what's more exciting and what I want to talk to you about today is COVID-19 and how COVID-19 is spread. So as a person who's not in the medical field, I've always felt I wish I could contribute to doing something that is related to COVID. Some of the faculty in our department who do sensors and do some bio have been involved with COVID-19 research, but on our end of the spectrum, how can you apply this? And about a month and a half ago, we got an email from the Utah Symphony asking for help in analyzing the environment on the stage of one or two of the halls in Utah where they do concerts. One of them is called Abravanel Hall, the other one Capitol Theater, and we essentially wanted to help them. They wanted our help in understanding the risk of exposure, assuming, let's say, the flute player or the clarinet player is infected, and are they going to infect everyone? And so we went ahead and just actually concluded one of the studies for this. That's for Abravanel Hall. This is a picture of Abravanel Hall on the right. As you can see, it's a beautiful, majestic place. Hopefully you'll get a chance to attend one of the performances there. And on the left, I'm showing the traditional arrangement. There's a bunch of clarinets, bassoons, flutes, oboes, and there's a certain socially distant arrangement required by the state of Utah. So up plus or more 6 or more feet distant from each other. And so that's the arrangement that was given to us. And the first thing we wanted to do is essentially conduct a simulation of, say, assume that all of the players are playing at the same time, and we're going to track the particle concentration, the mist, the exhaled particles that are coming out from the player. So we went ahead and got some measurements for the different wind instruments, and we put this into our in-house developed CFD code. And this is a depiction of the Abravanel Hall and with the different players. I'm going to run this for you. So what you're looking at are contours, iso contours of concentration. Red is 1 particle per liter, green is 10, blue and the bluish particles go up to 1,000. This is on a logarithmic scale. So obviously you see more blue near the instrument exits, as you can see here, and as the particles disperse, they get diluted, etc. But the first thing we notice is like there are some interesting structures going on here. You see up front there's like this recirculation of droplets, and this is kind of a very basic low budget simulation that we've done given the budget for the project. And so we are assuming a worst case scenario that all emissions contain virally loaded, all particles contain a virus. And so the next step we wanted to do was to just essentially look at the airflow inside that chamber, or the HVAC in other words. This is a high resolution simulation of the HVAC in the Abravanel Hall. And you can immediately see on the movie that I'm playing right now, there's the formation of these kind of 2 large structures spanning the stage from your left to right. There's like a vertical structure out front and one in the back. And then if you look out front into the stage, you see that there's also 2 recirculation zones forming near the boundaries. So obviously we cannot change the top recirculation zones. The risk there is like if you have a virus caught in one of those recirculations, then that's going to keep recirculating around until it evaporates. And because we cannot have the flow come across the stage into the audience, we cannot manipulate the HVAC in a way that flow goes from the stage into the audience. And one of the things we noticed, the first thing we noticed is that they had 2 doors, one to the left and one to the right of the stage. And if you look at the upper right figure over here, we said, hey, let's open those doors and run the AC at 80%. So the vents extract 80% of the, so inlet 100%, the vents, exhaust vents extract 80%, and the rest goes through the doors. And then we ran that with the players, and we did see some some change, but it's not what we liked. So we thought that opening the doors was important, but when you do the quantitative analysis, they make that big of a difference. And so we thought that we need a better mitigation strategy. And then we asked ourselves, why don't we move the instruments around? So for example, if the clarinets and the flutes are emitting a lot of particles, why don't we move them closer to the vents in the back? So what I'm showing here is a time averaged concentration of the spatial average in the breathing zone of the instrument. So we took a slice from 90 centimeters to 130 centimeters, averaged across that in the height, in the vertical direction, and then time averaged the entire simulation. And you can see on the upper left, there's the original arrangement that was given to us. Particle concentrations range over here from 0.1 to 1,000 particles, where you see per liter, where you see the red. And you see obviously here, there's like the drummer in the back and the percussions are in really bad shape. And out front, the cellos and the violinists, they're also in really bad shape, because all the particles just move in their direction. With the open doors, we did see a change, at least for some of the violin and cello players, but there wasn't much change for the back instruments. Then we thought, let's rearrange things. And one of the students working on this project is a classical music connoisseur, and so he came up with 4 arrangements. Arrangement 1 is shown here in the left, where he moved some of the trumpets, trombones to the back, and then moved the brass, the drums, and the percussions to the middle, where there's this where in the middle of the recirculation zone, if you remember the CFD. And another arrangement on the right, arrangement 3, which is what we recommended to Utah Symphony and Orchestra, We moved the clarinets all the way to the back, trumpets in the corners, and we see this beautiful, very reduced concentration profile over time. So the length of time here is about 15 minutes, assuming they're playing constantly nonstop. So anyway, I just wanted to get you excited about what you can do with computing in chemical engineering. If you are interested, remotely interested in doing computing, this is the place to be, at least at the University of Utah. And I know in the Western region, we have some of the best research being done here in computing. And I am actively looking for a PhD student. If you are interested, please send me an email with your resume and your interest, and we can rearrange some time to meet with you and talk about things and follow the guidelines suggested by Professor Scliar about how to go about this. And thank you so much for your attention, and appreciate your being here.